Hello, this is Shane Mueller, and this is Chapter 6 of the course Applied Statistical Analysis for Psychology and Human Factors. And we're going to be dealing with colors today and some advanced graphics concepts. You can download the course book from this website. There's a link to it in the notes. And if you scroll down to Chapter 6, you can follow this link. It'll be right by the video that you're watching, and here you can download the R code that is used to create these graphics here. And I right click or command click on Mac, and you can go save link as and then move it to somewhere convenient. I've moved mine to a convenient Chapter 6 folder within Documents, so I know where it is. And I've opened this within R, and so let's get started. So the first thing we want to talk about is the color system in R. And it can be, there's a lot of different ways to access it and a lot of libraries to help you create nice colors, because probably mainly because the default colors in R are pretty ugly, and we'd like to get around that. And R handles colors in a number of ways. First, it does for a normal plot, at least the first 8 numbers map onto colors in a color palette, and we'll talk about what the color palette is by default and how you can set it in a little bit. You can also name colors. There are color names, and there's, I think, just by running the colors function, you see there's 657 different color names: thistle, tomato, violet, red. And you can scroll through these. There's 100 grays probably. So there's gray 0 through gray 99, which gives you 100 different gradations of gray, or gray 0 through gray 100. There's also gray spelled with an AY and an EY. And there's a ton of different color names that you can choose from. So if you want to plot, pie chart of 3, C, 3, 4, 5. That's what you get by default. And then if you give it color equals, I could choose steel blue 2, tomato 3, and thistle 1. And it chooses, well, this is steel blue, this is tomato, that's a nice red, and this is thistle 1. So you can name hundreds and hundreds of colors. Mostly you would choose things like red, green, blue, probably black, but sometimes you can come up with nice color schemes just by looking through these names. There's also underlying, it also understands sort of the hex code often used on websites. And so if you do, which you can create with a number of functions, most easy is the RGB value. So an RGB means the red, green, blue, and the way the RGB in R works is you give it 3 numbers between 0 and 1. So R is red, I want it high in red, maybe 0.9. And then green, I want it maybe middling in green. And blue, I want it maybe low in blue. And so that will give you the appropriate hex code. I could then just use this as a color name as well. Or I could do this if I want to say plot, or maybe a bar plot so we can see it. R unit 5 color is equal to, and I can just do E6800. So whatever that color was, it ends up showing up here. It's the same thing I created here. The RGB also allows you to set transparency, which sometimes you can't really tell, but we'll show you how to do things as well. There's a 4th argument that makes it transparent, so if you overlay things on top of one another, they bleed through. So that's the basic color scheme. Now, by default, the numbers 1 through whatever map onto colors as well. So if I were to take some numbers and want to make a bar plot, I could say bar plot of, if I just do bar plot of data, it makes it gray. But if I do bar plot of data and tell it the colors should be 1 through 10, and there happens to be 10 numbers here, it will make these, let me run that one more time so we can see these beside one another. It will make them actually the 8 colors in the default palette. And then these 8 colors, and then reuse them. So you can see it starts with black, red, green, blue, light blue, or cayenne, or however you pronounce that. I don't know what this is. Yellow, gray, and black again, and it will repeat those. So there's 8 default colors. And so then, but that's just using colors 1 through 10. So those colors, numbers map onto those colors via a mechanism that's called a palette. But I could say, instead of 1 through 10, I can use the colors 2 through 11. I just took the 1 through 10 and added 1 to it. So now you see it sort of rotates it. So red is the first one, then green, then blue, instead of black being the first one, and it repeats after it gets through those 8. This is the most common way to use colors, just not worry about it too much and let the default colors dictate how the graph shows up, and that is probably why most of the time people think that the default colors in R are kind of default graphics in R are kind of ugly. It's not untrue, but it's probably due to a color scheme that just is not attractive, doesn't make a lot of sense, and is not really that discriminable. So there's a lot of ways to come up with a color scheme. Here's one idea that I saw on a blog somewhere. I can pick out any colors that match C. I'll call those C colors. So I take colors, and then I use this to look at any colors whose first 3 letters matches SEA, and I use that as a subset to pick out those colors. So if I look at C colors, it'll be, well, C green 1 through C green 4, then C shell, and then several C shells. So maybe this will be a color scheme reminiscent of the C. And there's a few ways to use those. So if here's a bar plot, and I can just use those colors. But then I can also set the palette. The palette determines how those numbers 1 through 10, or 1 through 8, or 1 through 16, or whatever the numbers are, map onto named colors. And I can set that palette to be anything using the palette command. So here I'm just going to say palette of my color names, and I'm going to put them, I do this just to give it a random order. I probably wouldn't necessarily want to do that every time, but you can see what order it comes in. So now I could do this matrix plot here. Let me zoom in so you can see it more. And it's going to use those for each series, these colors, but in a random order. And then finally, I don't have to specify, because I set the palette, I don't have to specify colors as a palette anymore. I can just set colors 1 through 10, and it chooses, whatever I had set to the palette by default. If I don't like the palette, I can reset it, or I can say palette, and I think it's default. And then if I do this again, it will go back to the original color scheme. So that's just some of the ways that R handles color palettes and colors. There are a few, not many, but a few built-in color scheme generators that will give us sort of color gradients. They're just built into R and are always available. And sometimes they can be handy to use. So one of them is called heat colors. So these are what they do is they have some functional way of defining a colors along a dimension, and then if you tell it how many you want, it creates a sequence of colors that map on some vector in color space. So heat colors, if I look at this, it shows, it's created several that map along some dimension, some axis in this three-dimensional color space. And it creates 10, but if I wanted 20, I could get 20. If I plot that, you can see that as I move to the right, it goes from red to yellow, so it looks sort of like a fire. The whiter it is, the hotter it is. Another example is terrain colors. It works the same, but this maps from sort of green to yellow to brown to white, and especially if you use this on sort of an image map, it can help represent terrain features in a map. The higher it is, it's more likely to be white glaciers, and the lower it is, it's more likely to be green. Topo colors is another one that is similar, but it goes from the lowest are dark blues, which represent the ocean, to higher levels, green for land, and then higher levels for high desert or something. And then this one, CM, gives you a mapping between this light blue cyan to magenta, which is the pinkish purplish color. So these are built in, and you can use those without loading any additional libraries. And so here's some ideas how to use them. Oftentimes you want to use color to represent a third dimension in a plot, a dimension that you can't otherwise represent in space. And so here's a set of points. This might represent, maybe you have an eye tracker where you're looking at where someone's looking on the screen, and so you can track how they're moving, maybe physical movement or maybe eye movement around a screen. And you want to represent maybe what happened earlier and what happened later as a color dimension. So I could give it colors, and I'll use the cm.colors to specify this mapping from blue to magenta and all the points in between. So that's kind of nice, because the more purple you go, the later or the earlier it is, and I could signal this, and I could add text that's all in black that gives numbers to reinforce that further. Here's another one where I could use the terrain colors and do the same thing, and now maybe I want to do, instead of black, because these are pretty light, maybe I want to do white, but then this doesn't show up. Here's a trick that's kind of nice. I'll plot the lines, and then I'll plot the points on the grayscale. And gray is another, although we have these colors, gray 0, gray 1 through gray 100, I can also use gray and say gray 0.5, and it'll return a value. And so I can give it a sequence between, say, 1 to, if I give it, I want 16 levels, 1 to 16 divided by 16 will be values between, really low, and I could even do 0 to 16 over 16, so this gives me a sequence between 0, which I think would be black, to 1, which would be white. So if I do this, my colors are this. And now, just to highlight it, I did the same points all in black to give sort of outlines to those circles. So you can see here. And now, since I saw that these are light and these are dark, and I want a light number, and these are light and I want a dark number, I could do I could reverse color and make the early ones white and the later ones dark. But then I'm going to get to a middle, so I could do the reverse white for my text, white to black. But that won't work in the middle, because there'll be a point in the middle that's identical for both the background and the text. So this is what I do sometimes. I'll create a vector that's just whites and blacks. Here I repeat white 8 times and black 8 times. and so use this for labeling. Let me see. And you can see now, you hardly notice this, but the numberings go from white on black until we get to the middle, and then they switch over here, and maybe you can try, maybe I want 7 and 9, that might be better, or I want more of light or more black, and right at this point the numbers switch over, and so you can always read the number. So by using color and then the opposite color, you can sort of overlay numbers and points pretty easily. So those are some of the color scales that are available in the default R package, and they're default R packages, and they're not many, and they're not really great. They're useful for some limited applications, but there's a number of libraries that have come along and provide a lot of other color things. So one is gplots, and gplots is a library we'll use more in this chapter, and it contains a lot of color things and also a lot of interesting graphics, and we already used it to look at error bar functions. So it contains functions like red, green, and a lot of different named functions. You can look it up in the gplots what all their color gradients are: red, green, green, red, blue, red, blue, red, blue, and then it also has this notion of a color panel where you can give it 2 named colors, or I guess 2 hex-coded colors, and it will create a vector between them that as a gradient between them, or even 3. So I'm just going to run this whole thing. You know, the details are I don't think the details are that important, other than if you want some type of gradient color, the gplots provides a lot of them to help you. Either you could do a rainbow or have sort of a single dimension that helps code differences in some variable. Various named, color panel, or red, green, or then there's also some rich colors with named palettes. So that's a handy thing to know, because these can sometimes, you want to create a red, green, but you don't have one easily that looks good. And these can be handy ways. You just load the gplots package and use that color scheme. And, sometimes you worry about the availability of these packages later for something like this. So I could, if I have a color scheme I want, I can just say, oh, I want green, red, 10, and print this out, and then I might copy this back into my file. I might copy, paste it here, and then I format this as a vector, and then I have these saved, and I don't have to worry about, I'd have to add all of the commas, but if I did this, I wouldn't have to worry about loading this in the future. Sometimes you go to a new computer and you just want to run the analysis, but now you need to load a bunch of different libraries, and maybe you don't have the internet at the time and you can't download them. So that might be a way of sort of making sure you have access to that color scheme always in the future, even if the maintainer of gplots no longer maintains it. So you can also use this to plot sort of a 2-dimensional thing. So what I've done here is plot, there's a couple things I did here. I used the rich colors, and I used 50 rich colors, which is sort of a rainbow. And I computed the distance from some arbitrary point, which happens to be 0, 0, to each of the points. So I've selected a bunch of points, and then I've computed the distance, just with Pythagorean theorem of, the distance to x equals 5, y equals 3. And I've used those to specify the color. So I say I want to plot this, each of the points, and then I'll use rich colors, but then I have to do sort of a rounding and flooring to get the color I want. So for mapping on the distance, because it's the biggest distance from here is going to be maybe up to 50, then I have enough colors for this to match onto. But I also did alpha is equal to 0.5 here, and in the RGB and in some of the colors you can always specify alpha. Alpha is a way that computer scientists have used to represent transparency in the color. If we zoom in, what's nice about this is you can see that when two lie on top of each other, it gets darker, and when a green and a blue lie on top of each other, it gets greenish blue, and so they bleed into each other. When you have a lot of points that lie on top of one another or that overlap, this can give you a better idea of how many points are in that spot as well, and it kind of looks interesting with this rich colors scheme. But this would be a really easy way to create transparency and allow you to overlay points to get a better feeling of the density of a bunch of plots. All right, so those are the colors available in Gplots, but that's not all. There is a library called ColorBrewer, and I just recently looked. They have a nice website, and I think these were originally created for attractive maps funded by the Department of NIST or Department of Energy or someone like that. And I think the original author her last name was Brewer, so that's how it got the Brewer. But it's sort of like color alchemy. So if you have to download this. So you can install the package like this, and it will take a little while to download the right things and then load the library. And there's some functions that it has for just displaying its color palettes. And it has sort of three types of color palettes. We'll zoom in on this. It has sequential, which are these, which give sort of one gradient. It has qualitative. I think these are the qualitative, which would be good for representing different multiple categorical levels. And these are kind of like the paint chips you get if you go into a paint store and say, here's a nice color scheme to use. So I call this the Martha Stewart of statistical computing. And then they have a number of ones that are divisive, that map between two kind of dimensions with usually something light or white in the middle. So these are the set of ColorBrewer palettes, and you can go to colorbrewer.org to see how they look on maps and browse them a little better. But we can look at individual ones based on their name like this. And some of these are really quite nice and give like a good impression of what things look like. So how do you use this? Well, it might be nice just to set the palette. So I can, this is not going to set the palette. I'm going to create a data variable called palette that I set brewer.pal 11 spectral. I want 11 levels of spectral palette. And then I set the palette to that, and then if I do a bar plot, it gives me that palette. And you can see how it looks. This looks a lot nicer than the default R colors already, and you might not even recognize it as R. Oops, what did I do? I think I just... I lost my window somehow. All right. Just a second, let me pause and get it back. All right, so I was able to reopen it. So we were talking about the palettes in ColorBrewer, and we have, I've got to probably reload ColorBrewer, and then I can, here you get one nice color. Here's a different scheme that sort of goes from brown to green, and you can see it still recycles the palette. I only have 11 colors in my palette, and so if I plot 22 values, it's going to recycle them and use them over again. Here's something that might be nice. You can see here that I've mapped the height of the bar onto the color. So the tallest ones are white and the lowest ones are red. And this is not too difficult to do. I've specified a palette here, and then I want an integer that maps the data into colors. And I notice, well, because the values are between 0 and 1, I'm going to multiply that by 10 and take the floor and add 1. So they'll be all mapped into 1 through 10. And then I've saved that palette, and I can just make the color in the bar plot equal to that palette, but the color specified by the data value. So that would be a way of adding more meaning to this, to use color to indicate something about height as well. All right, another a handy way to use colors, palettes, and color gradients is with image plots. We see this a lot. Here's sort of the default image, and I've just made a table with these first commands. That we've done this before to create sort of a 2D histogram. So I made this table, and that gives us the default, which is sort of this fire color. But I could use a brewer palette called Oranges, and that looks kind of nice. Or I could use blue. That also looks nice. I could use any of the built-in ones, topo colors, heat colors. That's going to be exactly identical to the default. And terrain colors. And now this, you could see, well, this kind of looks like a topographic map. This kind of looks like an island in the sea. So they kind of simulate those types of displays. So this is really something to think about whenever you do an image plot, because you can really set the colors and make it look very different than you might have expected to begin with. You can also use a grays here, the gray function we saw before, to make this a black and white one or a white and black one. Okay, so that's Gplots, and it's the Gplots and the ColorBrewer, and there is another one we talk about called ColorRamps, which sets colors, but I think we've sort of skipped over that. I don't know where I put that. I guess I have it hidden in here somewhere. Okay, but it's just another library to create different gradients of color. Now, you may want to think about one thing that let's see. Here we go. A lot of people have trouble distinguishing red and green colors, and especially some of the red and green colors that are defaults in a lot of plots. So it's kind of unfortunate if our plotting uses color on its own to discriminate something that, if you're colorblind, you can't discriminate. And if you're at all worried about this, people have said, here's a set of RGB space colors that are pretty good for colorblind people. And here's one that I found on the web somewhere. So you can use this as a good palette if you're at all worried about colorblindness and colorblind people seeing this. Maybe, especially if you have someone on your team who's colorblind, using this will make them happy. And, it actually looks pretty nice. It's kind of muted. It starts recycling after 8, but they're all pretty distinguishable from one another. And, they look pretty reasonable as well. So this will give you 8 colors that are distinguishable. And, so here's one. If I set the palette to this colorblind, now all my graphs I make will do that. You could also, if you're really worried about color, you could also use other arguments in bar plot like density and angle to do things like this. Here I've chosen sort of random angles and densities to give each thing a different set. And if I replicated that for the legend, then people would have two ways of discriminating, both a color and sort of a stippling pattern. So there's something you should think about when using color for when there's a possibility that it's important and you want everyone to be able to see it. Using the palette can be really nice because it means if you you choose a palette and then every graph you make sort of sticks to that palette, and it gives any document or report you make a nice consistent look and feel. So maybe I have some data I want to analysis on different years of students, freshmen through graduate students, and I have a bunch of different graphs over a whole document, and I can just at the beginning set this palette. Like, this is this color scheme I want. Maybe this is related to my school colors or your company colors or something. But then maybe someone doesn't like it, and I can just reset the palette to something that that person does. And without changing anything, now I have all the graphs redone with my new palette. So rather than hard coding colors schemes, you've set it up in a way that all your graphs will have that look and feel, and you don't have to do anything about it. And if you want to change anything, you change one line. So that's something to think about especially if you have a long markdown file and you want it to look nice. You can pick a palette like this at the beginning, and then all your graphs in that will have that look and feel sort of by default, and you don't have to fuss with it. Another thing to think about with color is that in many palettes there are dark and light versions of different colors. So here's that sea green we looked at before, and dark green. So here I've sampled a bunch of random points, and then for each x integer level, I found the mean of all the values, and I've drawn those as dark points. So this is a great way of indicating sort of these are related. They are part of the same thing, especially if I have maybe another swath up here. I can make those in a red or a blue and put a light blue and a dark blue. That can be a nice way of using color. Similarly, you can use pairs of colors, and here the ColorBrewer palette of paired will give me these pairs automatically, pairs that are related, so light and dark, light and dark, light and dark. And now in this case, the orange juice or the tooth growth data set, these are associated with one another, these and these are associated with one another, these each are a different dosage, and so these are vitamin C versus orange juice of the same dosage. The color shows that they're related to one another and helps, gives better visual appeal, but also helps you interpret this better. You can tell that they're related without having to draw lines and things like that. So we have previously looked at pie charts and how they're not nice. You can also, and so maybe other types of area charts are a little better. And you can make, using color and rectangles, you can make boxes on a grid really easily. So for example, if I do this, I plot type N, it will make a blank plot. It doesn't have any axis or anything. And then I can draw horizontal and vertical axes and start drawing rectangles. So here's a rectangle that fills the whole thing. But now the color scheme I've created has different levels, alpha levels, so they have different levels of transparency. And so unlike a pie chart that is mutually exclusive, this would let me make a chart that shows the proportions of different overlapping groups or factions. There's a famous problem within psychology about Linda the bank teller, or that's and so this can illustrate that. We've got some proportion of people who are bank workers, and some proportion of bank workers who are feminists, and the set of feminist bank tellers is smaller than the set of feminists, and smaller than the set of bank tellers. It's a subset, and this illustrates that subset using overlapping shades. So I didn't have to figure out what color to make this. I made a transparent pink, overlaid it, and it just sort of does the mapping automatically. All right, so that covers, other than I think the part in the chapter where we skipped the ColorRamps package, which is another alternative. That covers a lot of different ways of using color, making nice palettes, and sort of high-level ways of using color and thinking about color in your graphics. The rest of the chapter is a couple examples of more advanced graphics. And these are things that maybe you don't use them a lot, but if you wanted to recreate this on your own, it might be very difficult. I'm going to go over these really briefly because none of these are things that are critical for understanding R, but each of them could be useful in the right contexts. Let me briefly go over ColorRamps and I won't even use R for this. Let me close this, and in the book you can see section 6.1.5 quickly goes over ColorRamps, and ColorRamps has a bunch of functions that also produce palettes, from very much like the other color gradients we saw that you could use just as easily as any others. So there's nothing too special about these other than it's a small library that creates some nice color gradients that you could also use as a palette. All right, so back to these special purpose graphing functions, and I'm going to have to install gplots, I think, for this to work. And oops, what happened here? Install packages gplots. The package library, you can do this just with this text or by navigating here, and I'm also going to install one shortly called plotrix, and I don't think I have that installed already, so I don't need to install it. If you were working through the previous chapters, you wouldn't need to install it because we've used both of these. I need to make sure gplots is loaded. And so the first thing we're going to look at is a balloon plot. And a balloon plot is a nice way of representing crosstabs. So if you have two different categories, you have a crosstab. You often use this to use a chi-square test to see if one set of categories is dependent on another. And here we might say, well, let's look at all of the cats with different names and see if their names depend on the color. These are just fictitious data, so I don't know if there really are 261 cats named Dilly, but if there are, maybe mostly they're brown and orange. And but here you see cats named Bernard are more likely to be gray. This helps visually depict these cross tabulations, and it also does something in the margins where it shows you sort of the overall set, the overall size of each set if you sum them all up. It gives you the numbers as well, and there's a lot of different ways to tweak this to make it look nicer or try to make it look nicer. The interesting thing here is that you give it data, first all the cat names and then all of the colors, or first all the column names and then all the color names, but you have to do this for every cell. So you would organize this using like an aggregate function. So if I look here, you see that Jack is repeated for every row and color is repeated for every row. And you give it these three things and it builds this. You might expect that this would take, this could, I don't know, this might even take a table because all the information is there, but at least the version of running it I show here takes 3 arguments. Of course, there's other tweaks you can do to look at the different size. I can get rid of the text and use color. I can make the circles unfilled. And so this is kind of an easy way of looking at a cross tabulation, which is a really common type of data to collect. You know, you have multiple groups with multiple products and you want to look at the outcomes. These also don't really have to be counts. These could be mean values if that makes sense for the type of thing you're looking at. All right, the next figure we have, which I think is really nice and convenient at times, is called the gap plot. And so here's a case where you might need a gap plot. I've got, well, I somehow got rid of my margins, but I've got some points here and here and here and here, and these are numeric x and numeric y axis. And I would like to have cut out all the middle parts here and just show the high and the low, because maybe there's some relationships within this that this graph is really hiding because there's such a big difference across. So the gap plot lets you do that, and you can read the instructions for the details, but really you specify the values and then you specify where the horizontal and vertical gaps should be. And here we have 2 gap plots where we've shown the gaps in different vertical gaps in different locations. Here's a gap plot that's a gap on the horizontal axis, and I can plot lines on each of the points, and then I can, I guess, add this to another gap plot, the gap that adds the gaps on the vertical axis. So when you have situations where you have sort of little isolated pieces of clusters of data that have a lot of space between them, this could be really handy in those cases to help zoom in on it. One caveat, I think that if you try to overplot lines and stuff not using gap plot, it fakes all these axis numbers. It still plots on a normal R plotting palette, but it sort of fakes the numbers. So if you try to plot the numbers, it's not going to get it to the right spot. So you have to, if you end up doing this, you have to do all of your plotting with gap plot because it creates its own axis system underneath that. All right, another really handy one is bar plot 2. And bar plot 2 is in the gplots. Gplots is a number of libraries called with a 2 at the end, a number of functions with 2 at the end that sort of are improved versions of standard things, of standard plotting. I think there might be like an image plot 2 and things like that. So bar plot 2 is much like the error bar functions, and it has a lot of different arguments to control things. It will produce error bars by default within the plot, and also allow control for a legend that matches these sort of by default. So if you give it the arguments, so this is, I'm not sure if I like this color scheme, but it looks pretty nice. I've had groupings of rural and urban, male and female, across different age ranges. And so this helps to create something that can look nice, and I've got control over a lot of different small little pieces of this through the confidence intervals, whether to plot the confidence intervals, what the sub is here, the main plot color, the colors of these individual bars and things like that. I might choose like a color ColorRamps or a ColorBrewer palette here to give it a more professional look as well. MText and box are things that are available in the base R package, and MText I can use to add margin text to add more complicated horizontal values, and box I can put this around. I think this example was originally adapted by a student in this class based on some blog post somewhere, and so this might be something familiar that people have seen before if they're looking for bar plot, a nice bar plot in R. The band plot has, it's sort of like the plot we made earlier when we looked at color. It will plot a scatter plot and then plot sort of a smooth mean and plus or minus standard deviations. It's just by default it does this nicely, and then you have some control over the color and what the values should represent. Here we have another band and this smooth mean and smooth plus or minus 1 standard deviation. When you have data like this in a scatter plot, this can be a really nice way to illustrate with graphically sort of the range. And I know ggplot does something like this. Here we see that if you have sparse data, this smoothing is pretty bad. It's pretty sparse as well and doesn't look good at all. And here is one with sort of more custom graphing where I use this dark green and this light green to represent sort of a color theme here. Okay, so that's a band plot. It shows things as a band and plots sort of a smooth version of the mean and plus or minus standard deviations from it, which you can specify with different arguments. Okay, the next we have is the pyramid plot. This is out of the plotrix library, and we're going to look at the same. I think we looked at VA deaths here, and we can look at the same VA deaths with pyramid plot, which was designed specifically for, let's see, where's my pyramid plot? Designed specifically to measure demographics, to represent demographic variables. And in the book we've got, let's see. So this is handy because to make this on your own would be really difficult. And the default one doesn't look that great, probably because it's using, I don't know what color scheme this is. This doesn't look like the default one. And the values I have in this don't show up well in the axes. But the pyramid plot shows different demographic groups like 40s, 50s, 60s, 70s, 80s, and it shows, and you can't quite see, and then it shows proportions of male and female in each of these groups. And so this is death rate or death count in the VA hospital, I guess, for some time period of census by age and by demographic. Or maybe, I don't know, maybe it's Virginia. It would be, let's look at what it is. VA, so I'll do help, VA deaths. Deaths per 1,000 in Virginia in 1940. Okay, so it's not the VA hospital, it's Virginia. And so if you have demographic data like this, the pyramid plot can be really handy, and you eventually can make it behave by changing the gap size and changing the size of it. So now this maybe looks a little better. I can see per 1,000 people we have about 50 rural female deaths and 50 and maybe 55 or 60 rural male deaths in that age range, and so on. And here's sort of when I tried to make it as nice as possible using a good color scheme and labeling and stuff. This would be something acceptable for presentation, I think. It shows what happens over time across these different demographics. And VA deaths, I mean, these are the data. It's not really that complicated. But if you're looking at this, it's much harder to see the pattern than when it's visualized like this. So these are called pyramid plots because I guess typically if you stack these on top of each other and they take on a pyramid shape with age, if you're doing some demographics, then generally it'll get larger. Whatever you're doing will get larger or smaller as you increase the age. I had another demonstration of pyramid plot in this file that's not in the book. Here's another demonstration of a balloon plot for maybe different types of data, a larger matrix. Oh, and here, as I didn't show this before, so balloon plot will take a whole table. Doesn't require just the size, type, count. It can do the whole table at once as well. Here's another piece that we've talked about how terrible pie charts are, and it turns out that 3D pie charts are probably even worse. So here's a 3D pie chart. I guess it looks kind of professional. It looks, like you've got some nice graphics in here. And the Pi 3D, I don't even know what library. This might be a base R library. It might be in Plotrix or something. There's a lot of ways you can add shading and lines and stuff like that. And you can, let's see, add labeling. You can sort of take a slice out of it and expand it, I think. And overall, the problem with one of the problems with 3D pie charts is because you're looking down at this oblique view, the area in each pie doesn't even, like the amount of ink in each pie doesn't even map onto the number that you're trying to represent. And so it can be very misleading. If something is here on the side, it's not going to have the same amount of ink as 10% that's down here. So, here's some secret code for drawing 3D pie charts that are a bad idea, but sometimes you have to make one for one reason or another, and here's your chance. Okay, so I think that's it for the this chapter, but the only other thing I want to show is that there are actually, at the end of the chapter, I've described a lot of different plotting libraries and that are available, graphics packages and plotting libraries of note, that go beyond what the base library is. And you should be aware of these and look into them. And if you're in my class, you're going to be maybe taking one of these and giving a demonstration of it. And so, of course, ggplot2, or most people just call it ggplot, is one of the most popular ones, and it does some really nice graphics, and it handles some really tricky problems in base R packages really nicely, but it also can be really frustrating if you want really nice fine control and layering. So you can't do as much layering and stuff as you can do with the base R graphics packages. Plotly is a way of making graphics that live on the web and are interactive, and it can interact with ggplot. There's a nice maps package that allows you to make Google Maps and non-Google Maps and plot geographic information on maps. This is kind of older. I've used it for several applications, but Leaflet is really nice because it gives web-enabled maps. I think Plotly has some mapping ability too, though. So maybe these even interact or can use them together. There's a graphic library that I've used before that is mostly for like image processing, so you can take an image and blur it and stuff. That if you're into doing that or you have an application for that, that could be really useful. We've talked about gplots, and we've only looked at a couple of the functions. There's also a way of making Venn diagrams. Another function I found useful is the angle axis function, which allows you to plot angled axis labels. instead of vertical or horizontal, and give you a little more room to that. There's heat map too, which gives a better heat map than the regular heat map. So that's the gplots library, and there's a handful of really nice sort of more advanced graphics functions and sort of complete graphics plotting functions there. The plotrix library has dozens of sort of graphics helper functions for layout and things like that, and drawing, and also sort of all-in-one graphers. So like the battleship plot, this is kind of like a balloon plot with, or I call it a bubble plot here, but like a balloon plot with squares, bump chart, centipede, clocks, drawing circles and angles. You can make a Gantt chart, radial functions like radial plot, diamond plot, polar plot, create a stacked histogram. That can be really difficult to do with standard R histograms, but here's a way of doing it within one package. And what's called interesting figmaphobe labels. This is sort of a way of plotting text on top of points, but so that they're drawn away from the points and give you a little more space to look at things. They try to not crowd the points and move in a direction away from the nearest points to give a better look and layout. So these are some additional graphics functions and packages that are really helpful and can be really rich ways of, of displaying data. And so that is all. And the next chapter, I think, is going to start applying all of the things we learned so far, and we're going to start talking about probability theory and statistics and simple statistics, statistical inferential tests. All right, thank you.